Okay, so this is the video 2 of 2 for 11.3 paper 2 capacitance, numbers 6 through, I believe, 10. Yes. 1 through 5 was on the first video for solar problems. So here we have a situation, we have some bulbs, and I'm not sure what that has to do with capacitance. Maybe we'll find out later. Or rather, of course, bulbs could be connected to capacitors, but I don't see any capacitors in that circuit. So yeah, 6A, 6B, C, not related to capacitance. There might be information we need from those sections. We'll have to go to C. But, oh look, I see a capacitor, 6D. Now let's see what's up with that guy. So it says fully charged, we get the capacitance and the voltage. What's the energy? Easy peasy lemon squeezy. 1/2 CV squared. And we get 4.3 times 10 to the negative 4 joules. 6E. Now it says fully charged, a dielectric is stuck in there, and which has double the permittivity of vacuum. The original cell was in vacuum, so now we have a dielectric with double the permittivity of vacuum. And it said, what happened to the energy in the capacitor? Well, again, energy is 1/2 CV squared, and the voltage across the plates is the same, but the capacitance is not, because capacitance is permittivity times the area of the plates over the distance of the plates. Area hasn't changed, distance hasn't changed, but the dielectric sure has. And it says the dielectric has double the permittivity of vacuum. So we have 2 times the dielectric, so that would be 2 times the capacitance. Ooh, I got sloppy. I was looking at the mark scheme, and it says that the voltage halves. And so in order for that's a fair point, capacitance is Q over V. And so sticking the dielectric in between the two plates of the parallel plate capacitor doesn't change the quantity of charge because of conservation of charge. But it, so therefore, if Q is constant and I double C, by C is Q over V, if Q is the same and C is doubled, then the voltage must halve as a result. And that affects the energy because energy is dependent on both the capacitance and the voltage. So let's see what happens. So if you have the voltage, voltage is squared, so that would be a quarter, but then the capacitance is doubled, and so 2 times a quarter is 2/4 or 1/2. So the change in the energy is going to be half what it was. And yeah, it looks like calculate the change. It actually wants you to take half of the previous answer. Okay. So half of the 4.3 times 10 to the negative 4 means that the energy is now 2.2 times 10 to the negative 4 joules, which agrees with the mark scheme. Tricky with that current, with that charge and voltage. That slipped past me, but yeah, you have to consider all of the different aspects. All right. Yeah, see examiner's report. Most common answer involved doubling the capacitance without considering the change in the potential difference. And it said if you did that, you only got 1 mark out of 3. I think that's mean, but whatever. All right, 6F. What is the cause for the above change? Why did that happen? And then 6F says, why did that occur? And the mark scheme says because of the work that needs to be done inserting the dielectric into the capacitor. I guess. It says the examiner report says very few scored on this question. It doesn't even say explain, but I put in the explanation anyway. Energy obviously has to be conserved, so if work is done inserting the dielectric, that energy has to come from somewhere, and so it must come from the system, and so the system loses energy in the process. And that's the end of 6. So let's take a look at 7. Okay, so we have a battery, we have a capacitor, and when you discharge the capacitor, it runs the motor, which lifts the mass. We have the EMF of the battery. It says, what's the charge that flows through the motor when the mass is raised? Well, the charge flowing through the motor is the charge that was in the capacitor. So really it's saying, what is the charge in the capacitor? And so we get 0.09 coulombs for the quantity of charge. Okay, let's continue. 7b should be somewhere over here. So this includes some gravitational potential energy, but it also requires you to figure out the energy in the capacitor. And it says the motor can transfer 1/3 of that energy, but first we need to figure out what the energy is in the capacitor. Well, it's asking for the height of the mass can be raised, so let's start there. And it tells us that the mass is 45 grams. I'm looking for the height, but I gotta figure out that energy. All right, so we got the energy of the capacitor, 1/2 CV squared. 1/3 of that is the potential energy. Slip that in for mgh and solve for h, you get 0.25 meters. That would kind of be a neat setup. You could figure out based on how high the mass goes, like knowing the properties of the circuit and the properties of the mechanical system, you can figure out the efficiency of the motor that way. Like if you measured the height and you knew the capacitance and the voltage across the capacitor, then you can compare the two different energies. Anyway, 7c. Alright, so adding in a capacitor in series, when you add them in series, you follow the reciprocal rule. So if you add one more capacitor that's identical to the first, it's not twice the capacitance, it's half the total capacitance. Now, what does this have? What effect does it have on the height? Well, if we have half the total capacitance, that's going to have the energy. So the potential energy is 1/3 the capacitor energy, but if capacitor energy is directly proportional to capacitance, so if I have the capacitance, I have the energy. And the potential energy, of course, is mgh. And so if I have that potential energy, I'm going to have the height because the energy and the height are also directly proportional. Now, as for the time it takes, the discharge time on the capacitor. All right, so yeah, half the height. But then the time, even though it only goes up halfway, it's going to take less time to raise that mass. It's going to happen faster because that time constant has decreased. The time constant, the time to do to discharge 1/e of the capacitor is reduced because the capacitance is reduced, so the time constant is reduced. So if the time is reduced, then it's going to actually go faster, be raised quicker. And that's it on number 7. Now for number 8. Just to comment on the mark scheme, I don't know why to say allow 6 millifarads. Maybe in calculations, I guess. But it doesn't say calculate anything, it just says comment. So yeah. And then, yeah, there were actually 2 things needed to comment on, but the third mark was the fact that you would need to say that the total capacitance is halved. So that's kind of like your starting point. That was the third mark. Actually, the first mark, really, and then half the height in less time are the other 2 marks. Okay, we have number 8. 2 parallel square plates separated by vacuum. We know their dimensions and we know the capacitance. And it says, what's the distance between the plates? I stuck the units in there for E naught. It's a little tiny, but they're there. We got picofarads, so that's 10 to the negative 12. And when you run the numbers through, you should get 1.3 millimeters for your distance. Yeah, 1.3 times 10 to the negative 3 meters. Sounds good. All right. 8b. Capacitor is put on a battery, 16 volts. What's the magnitude and sign and charge on plate A when the capacitor is fully charged? Well, I can tell you that the sign is negative because based on the orientation of the cell, I can see that the negative terminal of the cell is on the bottom. So plate A is going to be negative and the other side is going to be positive. As for the amount of charge, that needs to be calculated. So when you run it through, we get 69 picocoulombs, 6.9 times 10 to the negative 11 coulombs. Okie dokie, let's keep going. 8C. And then it says, fully charged and the space between the plates is inserted with a dielectric of 3 E naught, whether the magnitude of the charge on plate A increases, decreases, or stays constant. So there, for 8C, if you slip the dielectric in, putting the dielectric in increases the capacitance, because C is a dielectric area over D. And since the capacitor is the only thing attached to the battery, it's the same, voltage is the same as the battery. So if the voltage is constant and capacity increases, then the charge increases too. 8D is an 11.2 question, as is 80, and that brings us to 9. So for 9A, we have the information. We have an area, the distance, and the permittivity. C is epsilon A over D. Plug your numbers in, 6.6 times 10 to the negative 7 farads. 9B, that's pretty simple. Why are there 2 marks? It's a pretty basic question. Yeah, it looks like 1 mark for the equation, 1 mark for the answer. All right, whatever. Yeah, C is Q over V. They give you Q. C is what we just calculated in 9A. And so, yeah, V is Q over C. So you have 3.8 times 10 to the 7 volts. 9C, another pretty straightforward guy. 1/2 CV squared. NOC, NOV. Don't forget to square the voltage. 12.8 times 10 to the 8 joules. And it's 480 Michael Jacksons. Alright, so for 9D, we do the Q is Q naught e to the negative T over tau. Put in the 18 milliseconds, tau is 32 milliseconds. Put in Q naught is 25 coulombs, and then the charge after the fact is 14 coulombs. Be careful when I say 14, why isn't it 11? Because 14 is the charge after. If charge initial is 25, charge after is 14. Because what's delivered, the transfer that causes Q final, is 25 minus 14, or 14 minus 25, whatever. The amount of charge is 11 coulombs. That's where the 11 coulombs comes in. And then 90 is I equals Q over T. That's super basic. You just do 11 coulombs over the 18 milliseconds, you get 610 amps. But that's not a 11.3 question, so I'm just going to skip it for now. I'm going to focus on the capacitance questions. Anything else for 9? Yes, F. What does it say? And then for 9F, it says, assumptions that a thundercloud system may be modeled by a parallel plate capacitor. We'll look at the mark scheme. Base of the thundercloud must be parallel to the Earth's surface. Base must be flat. Base must be very long compared to the distance to the surface. Basically, you want your model. So yeah, similar to the wide flat parallel plate setup, largish area, not too far apart. I don't know that I would use the word largish in an actual answer, but this is kind of like more for you. But like see below, any one of these responses makes sense to describe a system similar to wide flat parallel plate setups. Last but not least, we have number 10. All right, 10A. I think there's a typo in the mark scheme. This is 22 millifarads, and it says to answer the question is 1/2 CV squared, which is what I did, and then it said 1/2 times 0.22 times 24 squared. But 22 millifarads is not 0.22. It's 0.022. So I think yeah, 1, 2, 3. So yeah, 22, that's 0.022. So I think that's a typo. They also didn't give an answer. They just said equals joules. But whatever, I just did it in my calculator. I got 6.336, which rounds to 6.3 when you consider significant figures. Let's move on. And then 10B wants the time to completely discharge as a function of voltage. And it says the capacitor is completely discharged when the potential difference across it has fallen to 0.24 volts. And then Yeah, so we do V is V naught E with negative T over tau. Tau is RC, so that's 0.176 seconds. Throw our numbers in. For V after is 0.24 volts. V naught is 24 volts. Don't forget to take the natural log of both sides to get rid of E, and we get 0.81 seconds in the end. 10C specific heat capacity, we're not doing that. Question about the heat capacity and thermal energy losses, not really an 11.3 topic. All right, so then that's it. I thought there was more to it. 10D. All right. So that is the remainder of the 11.3 paper 2 questions. Here was the last guy, 10B. Thank you.